Hi, welcome back. So last time, I have to scroll back a bit more, we started talking about random BSTs, the good old plain vanilla binary search trees, and we started to analyze them in some detail if we have all insertion orders equally likely, which is not exactly what we expect to have in practice, but we will today see two strategies how to enforce the same behavior, but by randomized algorithms. But before we come to these randomized procedures, we'll go on to analyze the random BSTs a bit more, because a lot is known about them, and it's simpler to state in the random BST point of view, but you should already keep in mind that the results that we're going to show now will in the end apply to these cool randomized data structures that we cover at the end. So it's not supposed to mean that we're studying this kind of esoteric data structure, random BSTs, under this assumption that's never going to hold in practice. It's just a preparation for what's to follow. And the last thing that we did last time was a first precise result, the expected depth of the leftmost external leaf. So just to repeat that, here I draw all the different binary search trees for 3 keys, and we will always use circles for internal nodes and these little squares for the external leaves, which are essentially null pointers if you represent the tree in the usual pointered way. But it might make sense as the mathematical object to include these external leaves so that we can talk about them and number them. So to be specific here, this is the first internal, second internal, third internal leaf, just numbered in order. Which nicely corresponds to exactly the key value if we have the universe of the numbers 1 to n. And we also number the leaves, the first, second, third, and fourth leaf. There's always one more than internal nodes. And these correspond to the gaps between the keys. So if you like, then this leaf could be assigned the value 1/2, then 1.5, 2.5, 3.5. But we'll number them starting with 1, which is somehow more natural. I just mentioned it again because sometimes people start counting at 0 for the leaves, which also makes sense, but it makes a difference for the following formula. So I promised last time that we will extend this kind of boring result that only talks about the leftmost external leaf to any external leaf. And in fact, this is the first thing that we're going to do. We now take the kth external leaf. So we're interested in this quantity. I'll just write it graphically as such, a square with a k. So it's the kth, as I just said, counting from the left. And then the depth of this thing, which is the number of edges on the path from the root to this leaf, which coincides with the number of internal nodes on the path from the root to this leaf, which coincides with the number of comparisons you would need if you follow this path in the tree. So if you search unsuccessfully for any value that falls into the gap that corresponds to this leaf, you will exactly need that number of comparisons. So that's why this quantity is of interest, okay? The number of comparisons for an unsuccessful search. Unsuccessful search. So that which terminates in this leaf. Well, as you know, unsuccessful searches are the basis for insertion, at least in binary search trees without any balancing, and also in most other schemes. You first unsuccessfully search an element, then you find a leaf or a null pointer where that element should have been if it would have been in the tree, and then at this point you insert a new node. So this number of comparisons for the unsuccessful search is also a building block for the cost for inserts. Well, and deletions are similar, but talking about successful searches, this is what we'll cover in a few slides. Okay, the cool thing is that if we have the kth leaf, we can exactly express the expected depth using harmonic numbers again. So recall that this was 1 plus 1/2 plus 1/3 and so on up to 1 over k minus 1. And you might wonder why this is the case. If you remember, we did last time, we saw that there's a quantity in permutations, the number of left to right minima that played a role. And this quantity had the expectation hn. So the number of left to right minima in a permutation of size n is an expectation is hn. And it looks like something similar occurs here. And that's indeed the case. Oh, by the way, I'll comment on that plot in a second, but let's first do the proof. Assume we have, okay, so here's our leaf k. And then there's a certain path in the tree that leads to that leaf. Oh, sorry. It can never go more to the right than this. I'm trying to draw the nodes so that if you follow the vertical lines down, then the labels are sorted. Okay? You can always draw a binary search tree like that, where you just say the x-coordinate is the key value. That gives you a nice layout for the tree, by the way. And that's exactly what the binary search trees are like, so this is absolutely nothing new. So say the path looks like this. And if you follow from k up, you cross this line a few times. And a trivial observation is that if this is the line, the real lines, say if these are numbers, then what we're doing is kind of a binary search, and every node tells us, gives us a boundary, and these get better and better, and then at some point, well, the gap here is a bit large, so we know that there can't be any internal node in this area, otherwise it would have been in this part of the tree. Now what this immediately tells you is that all these ever have to get closer to that dashed line. And that's again something similar to these left to right minima. Okay, maybe my example is a bit unfortunate. Let's add another node here. I'm sorry, so that we have at least 2 here. But on the right side, these are all left to right minima in the sense that they are the smallest node on the path that we have seen up to now, conditioned on the fact that it lies to the right of this dashed line, right? So these nodes are exactly the left to right minima. If we only look at the keys greater than x. Well, so I should add that, say this was an unsuccessful search for x. Okay. Just to have a value to talk about. The gap itself is not a value, but you can pick any representative value from that. So this is exactly the left to right minima if you delete from the insertion order, which is a permutation. If you delete from that permutation all elements to the left of the line and then count the left to right minima, you get exactly these green nodes. And a symmetric thing is true for these on that side. This These are the largest nodes. That are on the other side. And then by the same, well, one thing that's missing, the total number of these keys is just k minus 1. That's if you count from the leaves. If you start counting at 1, leaf 1 is the leftmost, which has 0 internal nodes to the left of it, so it's k minus 1. And here you have n minus k plus 1, which is n minus k minus 1, right? So that means this depth of the kth leaf is exactly this left to right minima. And if we're looking at the expectation, it's just the sum of these two. And in fact, these are even independent, because in a random permutation, the numbers smaller or larger a certain value are, in a sense, independently ordered. We'll come back to that in a second. And yeah, one thing I wanted to add, we can do that in a second. So this finishes the proof. Okay. It's again one of these proofs that's easy to grasp if you look at the picture. We will see you can also derive it more algebraically if you define indicator random variables, but I think in this case this is transparent enough. Okay, to this plot, which is supposed to illustrate a bit what this actually means. What I plotted here is this exact expected depth, and then divide by hn. Why that? Because that's just the minimum of all of these. If you set k to 1, then you get the depth of the leftmost leaf, which was exactly hn. We showed that last time. So this is just a generalization of that result. You can insert k equals 1, you get the same thing then. And what I plotted is this for different values of n. So this is for 100. That was always going up in powers of 10. And what you see is that these get ever more edgy. And actually the limit of this is just a line at 2 with a very steep drop down to 1. But if you oh yeah, I didn't say what the x-axis is. So the x-axis is k divided by n. Maybe you've guessed that. So it's a measure of how central the key in the tree is. And the result says that the more extreme a value you have in the tree, the less is the depth of the corresponding leaf. But the difference is never more than a factor of 2 if we talk about the expectation. You can sum up all of these and divide by n, and then you get the average depth. Or if you just sum up, then you get the external path length of a tree. And the external path length is just the sum of the lengths of all paths to all external leaves. And if you sum that up, then you can simplify these sums over harmonic numbers. That's yeah, something we don't have to do here. And asymptotically, you can give a very precise approximation if you like. It's essentially 2n log n and then the linear term and so on. And in fact, you know the precise value, so you can give it as precisely as you need. And a second thing that's maybe interesting, if you take the alpha nth leaf, so you fix a certain ratio alpha for k divided by n, and then you take the alpha nth leaf where you keep that one fixed but let n go to infinity, then the depth is exactly 2 log n, which is what I draw here. That's the line. And it only goes down from 2 if this alpha can depend on n. Okay? And if you, in the extreme cases, set it to 0 or 1, then it's 1 ln n. That's what we've shown before. Something I don't want to prove in detail, but it's good to know, I think. These left to right minima in a permutation can be expressed in an alternative way. I just want to sketch it very quickly how this looks like. If a1 up to an is a permutation, so this is just the numbers 1 to n in some order. You might know that you can bijectively represent such a permutation as an inversion table, where this bi is the number of inversions, so the number of out of order pairs, where for bi the second index must be I. So in less cryptic form, it's the number of values that's in the permutation come before left of I that are smaller, that are larger than I. Okay? So inversions means a pair that's out of order, so large comes before small, and bi is exactly the number of inversions where the second component is I. So it's the larger elements that come before I. You can prove that there's a bijection between the two because you can just compute one from the other in a unique way. But the cool thing is if now A is a random permutation, so chosen uniformly at random, then the bi are all independent and they have a certain distribution. Well, here we can already say the bi must be in 0 n minus I. This number of values to the left of I that are greater, well, it can be 0 or it can be anything, but certainly not more than n minus I because there are just no more larger values. Well, and then if A is a random permutation, then this is exactly a discrete uniform variable with that range. And the great thing is that they're independent, which is helpful because then the left to right minima of A are exactly all entries B that have their maximal value. Because if all greater ones are to the left, this is that means that then all positions to the left of I are this. Then I must be the smallest at this position. I'm sure that the correspondence is true, but maybe my explanation was not. So my problem is that just because I know that all are on that side, I think this actually expresses a right to left minimum, not a left to right minimum. So what this says is all numbers that are larger than I are to the left of I. That means if I come from the right, I first see I and then all larger ones.
Well, describes like the straight paths, how many of them are there?
Right. Oh, this is mind bugging. So all larger values are to the left.
It also says everything on the left is larger, right?
Yeah, but that's not necessarily true, right? So if I come from the right, then I never see something larger before I. So it's a right to left maximum. And by symmetry, you can certainly transform it to the other, but so this means all values larger than I are to the left. So if you scan from the right, then I is a largest value at this position, because all larger values are to the left. Okay. Yeah, maybe I'm overlooking something. But it's certainly the same kind of quantity by symmetry. And the good thing about these are that these events are independent. Okay. So this number of left to right minima is the sum of independent indicator random variables. And for these, you can use this general Chernoff bound, which gives you a very sharp concentration. So a formal proof would actually need a slightly more general Chernoff bound than the one that I stated. It's not the setting that is too strict from the bound that we have, but we had two types of bounds, if you recall, that one that we proved, and then a second one that is nicer to use that I didn't prove. And there this parameter delta is a bit too restrictive, but you can actually lift that restriction. It's not necessary. For the next iteration of that course, I'll correct that slide. So just to give you this hint, because these are independent indicator random variables, you can do something like Chernoff, and that means that you're pretty concentrated. So what that means for these expected results that we've shown about the depth is that they're not only true in expectation, but actually the depth of any leaf is with very high probability within a constant factor of this. So it's logarithmic, the depth is logarithmic with high probability. And all this might sound a bit familiar to you, the numbers 2n log n and this high probability depth and so on. The point is that there's a close connection to Quicksort, for which we studied the depth already. So I mentioned that before, but didn't go into further detail. So for one thing, we have the random BSTs, where we say all insertion orders are equally likely. And then we had the Quicksort recursion trees, which are also random trees because we considered randomized Quicksort, where we pick these pivot values uniformly. So that means in terms of the tree, the root is chosen uniformly from all keys in the subtree. And in fact, these two distributions of tree shapes are the same. And one way that you can see why is if we have a root and then the subtree with all keys smaller and larger, then the shapes of the two subtrees are independent, because if you start with a random permutation like this, what will happen in the tree and in Quicksort in the same way, you make this the root or the pivot, and then all smaller values will contribute to the left subtree and the other ones will contribute to the right subtree. And this splitting of one permutation into these subpermutations where you just keep the relative order of the numbers. So this is a bijection. And then you could even rename these if you like, but we don't even do that in the tree. And because, well, this is a bijection because you can just count that the number of different options of triples here gives you n factorial again. Maybe we want to very briefly do that. So there's n factorial different versions of these, you know that. Now if you, well, there's the pivot value can be something between 1 and n. That's the first thing here. That's k. And then for the rest, you have to pick these positions. So you have to pick from the n-1 remaining positions a subset of size k-1 because so many values are smaller than this value k that you have chosen for the root. So that's the positions for the left subtree permutation in the large permutation. And then these subpermutations here are of size k-1 and n-k. And they are, again, random permutations. So there's k-1 factorial and n-k factorial, many of these. Put this to the top. So that's the left and that's the right subtree. And if you just compute these, so unfold the binomial coefficient, then you see that most cancel. So this is the same, and these are the same in disguise. So that means you sum n times n-1 factorial, which is n factorial again. So there's the same number of these as these, which means you can build a bijection. And from these, well, another way to state that the probability for a certain shape of the tree, which is also something we didn't mention yet, so that's why I wrote it down once more. So the probability for a random BST to have a certain fixed shape Tn, so this is a bit sloppy, the notation, is if it's just a single external leaf, then there's nothing to do. It has to have that shape. And for any larger number of keys, you have to select the pivot or the root uniformly from all the n keys that you have. And then you multiply by the probabilities of the subtrees, which are independent by this argument that you can just reduce the permutations to these two cases. So for any specific tree shape, you can relatively easily compute what the probability is for a random BST to have that shape. It's not something we're going to use a lot in this course, but it might come in handy at some point in time. So I made this argument to convince you that quicksort recursion trees and random BSTs are actually the same distribution of tree shapes. And that means we can use the results that we know from quicksort and apply them to random BSTs, which was the height is logarithmic with high probability. And we know from quicksort that the expected internal path length, we talked about external path length before, which is the depth of the leaves summed up, where you can do the same thing with the internal nodes, and that's just the comparisons in Quicksort. So here's something that's worth sketching one more time. So the tree continues, of course. Let's take this element. It has a depth of 2, counting the edges. And so what this is saying is that there were 2 comparisons that involved this element x when Quicksort was run that produced this recursion tree. And the reason is we started at the roots with one partitioning step with a certain, I don't know, A, B, with a certain pivot A. And in the course of that partitioning step, we compared A to X and decided X is somewhere to the left. Then in the recursive call, we had another partitioning step where we had a pivot B, and we compared X again to that. And in the next step, actually X was made the pivot. And all the comparisons that we're doing in this step are charged to the other elements, not to the pivot. Otherwise, we would be double counting. And that's why if you sum up over all internal nodes in the tree, you get exactly the comparisons in Quicksort, just in a different order, right? Well, and then you know that the comparisons in Quicksort are this, given by this term, which is asymptotically the same as the external path length, but it's a bit smaller in the linear term. There's an n missing. Okay, so we talked a lot about these external leaves, and we've seen that with this Quicksort analogy we can get the path length, but actually we can give as precise a result for the depth of an internal node as we can for an external node. It's a tiny bit more complicated, but not really much. And because this is also going to help later, I'll give that. The point here is not so much to have the second result, but to introduce these tools, these indicator random variables that we will use later again for, well, a more peculiar kind of parameter of trees. So we consider in a random BST these variables A, which just stands for ancestor, and x above y should just remind you graphically that this says x is on the path from the root to y. Okay? And if this is so, then this axy should be 1, otherwise 0. And here we make the convention that a node is not on the path to itself, which is, I mean, it's sometimes it's more convenient this way, sometimes more the other way. It's just the convention that makes it work out easier here. And then we have 2 other interpretations of this statement and the result on the distribution. So the first says x is above y in the tree exactly when among these sets of keys x was the first that was inserted into the binary search tree. So why this strange notation? Just because I want to allow x less than y and y less than x either way. So this union is always just min xy up to max xy. Maybe it would be, it's maybe silly to write it like this. Up to point. So that's the first statement. And why is that the case? So, okay, I would like to have some room. So I'll first discuss the statement, then we'll quickly argue why it's true. And the second says that these two are compared by quicksort in a step where x is the pivot, exactly if this axy is 1. And that's essentially just rephrasing the first step. If you go to this here, in this case, we would have small a is above x, right? Well, small a is boring because it's the root. Let's take b. So this is 1 in our tree here. And it's 1 because it's above this in the tree, and also in the partitioning step here where b was a pivot, x was still part of the sublist. So x is part of the subtree of b. That means it was compared to b in that partitioning step where b was the root, the pivot. Okay. So this is actually nothing that needs a separate proof. It's a consequence of this correspondence that we've discussed before. And the third thing is a consequence of the first. The probability for x to be the first among so many elements, which is just this number, is just 1 over that, because roots are always chosen uniformly. That was the defining property of random binary search trees. Okay, I'll come back to the remark in a second. But let's give again a picturesque intuition. So there's a tree where we have these nodes, and there's a larger subtree that corresponds to x. So here we assume that x is less than y, but this doesn't really make a difference. So we can make a case distinction on which of the keys x plus 1, and so on up to y was first inserted into the tree. And then we can check what the consequences for the axy are. So if y is inserted first, that means that for sure x is below in the tree than y. Maybe not a successor of y, but it can't be above y because we inserted it before. Okay, so it can't be on the path from the root to, so x cannot be on the path to y, because if it was, it must have been part of that path when y was inserted. So certainly axy is 0 in that case. Now if some z strictly between the two was first inserted, that means that x and y are on different sides of z in the tree. And then the same result is true. We can't have that x is on the path to y because they were separated by z. And the last case is that x is inserted first, and we have to show that then y actually x is on the path to y. And at the time when we inserted x, all these values that we have not yet inserted, right? All other values from this set correspond to the same gap. Because there's no value inserted that could separate them into several gaps. And that means that all of this set, all values eventually end up in X's right subtree because they are larger than X, and they're just a bit larger than X, so there can't be another node that separates them from X. Well, and if they're in the right subtree, then certainly Y is one of them. X is on the path to Y. Okay. Now something we'll use later is a slight generalization of this. I can take two nodes, Y and Z, and ask whether X is a common ancestor of those two. Okay, so I was a bit... It not necessarily has to be the least common ancestor, not the first one if you follow the paths, but just any one. So X is on both paths. In a sense, this is equivalent to saying it's on both. But the point is why we're not simply using this product. These two variables are not independent. And so evaluating products will be tough, whereas this is something we can explicitly compute. Just by the same kind of arguments, you exactly have this property if among all these keys that fall into this range, so where we take the smallest as left boundary and the largest as right boundary, whichever one it is, if X is the first one among all these elements that was inserted in the tree, then we have this property, and otherwise we don't have it. It's with the same case distinctions that we just did. You can show this. Okay, now we can put this to good use if we look at the depth of the internal nodes. Okay, so this was, we had the result for the leaf K, and now we're looking at the internal node K. So I'll write it with a circle. Okay, if you look at the result, it looks very similar, but not exactly the same, of course. And well, even though the expectation is very similar, the distribution is not quite so similar. I'll come back to that. So what's the depth of this internal, the kth internal node? Of course, we would like to express that using our fancy new tool here, these A's. Well, the depth is the number of edges on the path to this node from the root, which is the same as the number of internal nodes on the path to this element if I leave out the element itself. So I can just sum up a few of these A's, namely all nodes X that are above K. And here it comes in handy that we just defined AKK is 0. So here we can simply sum over all values for K if we like. And for the expectation, you can simply insert what we know, right? So
in the sum, you probably want X to go from 1 to N.
Oh, that's right, yeah, sorry. K is usually used as a summation index. Should have stick to that. So the expectation of this is just the probability that it is 1. It's an indicator random variable, right? So, okay, let's do super slow-mo. Well, then we know that the 1 is never true, so let's split it up. Oh, come on. X from 1 up to K minus 1. Now the probability for this, if you remember, was given by the size of this set, right? Which then here means K minus X plus 1. And then you have the part where X is greater than K. And then you can just massage this sum a bit. So the first one we can sum in reverse, because so what's the smallest value we can get down here? So say we want to write it as 1 over I, and the smallest we can get is k minus 1 plus 1, so we start with 2. And the largest we can get is k minus 1 plus 1, so it's k. And in the second sum we do the same thing. We would like to write it in this form. What do I have to do? The smallest value you can get down here is you insert k plus 1, that's k plus 1 minus k plus 1, it's again 2. And the largest, if I insert n, then I have n minus k plus 1. Well, these are our famous harmonic numbers, except that we start at 2 instead of at 1. So there's one summand that we have to subtract. And that's 1 over 1, so that's just a 1 for each of the sums, right? So here's our result. Now, one remark is that in this case, these indicators are not independent. At least it's, well, they're not obviously independent, and I don't think they are. So at least there's no simple trick how you could use this representation for the depth of the internal nodes to do the same kind of Chernoff bound trick that we could do for the depth of the leaves. And that's why the distribution, although the expectation is kind of similar, the distribution is a bit different. And if you think about it intuitively, it makes at least a bit of sense, because internal nodes can also be high up in the tree, which means they can be a good deal smaller than the expected value. On the other hand, this distribution is still kind of concentrated, because you know that the majority of the leaves, more than half of the leaves, must be in the lower levels. And if the depth is essentially logarithmic again, the lower levels can also be too spread, so too much spread. So it's still kind of a good distribution. This remark contains a little curiosity. If you sum the same thing but flip the two arguments here, n, then you sum over all x that are below k. So that's just the size of the subtree of k. Maybe plus 1 because we didn't count k itself. Okay. I guess I just forgot that. Let's add a 1 here. But
you probably didn't, because it's hk instead of hk minus 1.
No, you have to compare with this. And I just remember that I copy-pasted it, which was probably by mistake. So there's an off by 1 because this sum does not count k itself, but as the root, it's part of the subtree of itself. Okay? Never mind, this is not an interesting result for our application, but I found it kind of curious that the same number is the expected depth of an internal node and the size of its subtree, right? I think in this case it's nothing more than a funny coincidence, and it's only true for the expectation, but still I found it kind of remarkable. So here's the remark. Okay, there's a lot more you can say about random binary search trees, and I won't go into detail here. One of the fancy things is that you can compute the expected height, so not just the depth of some fixed node, but the maximum over all of these, to a very precise asymptotic estimate. And then there's a lot of results. So you can compute the exact number of leaves at a certain depth. You know the exact number by some combinatorics. And then there's a lot of results that talk about stochastic convergence of all kinds of quantities. They're extremely interesting from a mathematical point of view, but I think the conclusion for our course here should be that we're actually quite happy with the performance of plain BSTs, because they're on expectation and with high probability very balanced. The point is just that we can't rely on random order in any application. Okay, here's something I just wanted to show you. Let's see whether this works without me changing to the okay. Yeah, you will see the nice picture that I googled there in a second. So these are videos that Bob Sedgwick created, and this is just a random BST as it grows if you randomly insert nodes. And if you keep, oh, that's not very helpful. If you keep doing that, well, you can keep track of the average depth and of the best depth you can achieve with a completely balanced tree, and you see that they hardly differ. And also the height of the tree is not so much different. So if you just randomly insert nodes, then the tree is pretty balanced. Interestingly, this is no longer possible if you also allow deletions. At least if you use the usual deterministic algorithm for deletions, which is Hibbard's deletion. So that's you search for the node that you want to delete. And if that's a node X here, then you replace it. Okay, I don't recall which one Sedgwick uses. Say you take the maximum of its subtree and then you replace it essentially by that node. And then you have deleted X. That's a fine algorithm. It's correct. The problem is that it systematically skews the shape of the tree, because you tend to subtract things from the right, but you never do that from the left. And that means that if you continue that in the long run, you will have a square root depth of the average depth or height of the tree instead of logarithmic, which is a huge difference, right? And I think it's not even possible to repair that by saying, instead of always taking the max of the subtree, I could also take the min. You could just flip a coin and do either way. That also doesn't help. That's not good enough. And there's the second video where he demonstrates exactly that. Let's watch it from the beginning. So this starts with a random BST that's built according to the procedure above. And now he alternatingly deletes or inserts a random node. And you see that the tree becomes kind of left-leaning, because you tend to delete on the right. And well, we're already a good deal away from the values that we had for the random tree. It's not that it completely explodes, right? But you see that the root is almost the max at many cases. So this is an interesting effect that's been bugging people for quite some time. And I think it is still an open problem to find a deletion algorithm, a deterministic one, that avoids this problem. Now we'll see hopefully later today. I'll have to speed up a bit, I guess, for that to happen. We will see a randomized algorithm that avoids this problem in a very clever way. So it's very much like Hibbard's deletion algorithm, but it just uses randomness cleverly to avoid that problem. So I'd argue that plain BSTs are fine, but they have two defects. there's the worst case, which we would definitely not want to have. And there's the issue with the deletions. And randomization can elegantly fix both of these defects. But of course, it's not the only thing you can do. In fact, it's a very well understood problem, and you certainly know at least one kind of balanced binary search trees, certainly some example of a height balanced tree. And there's a few others. Maybe you haven't seen all of them, and I think all of them are kind of cool. But still, all of them also need some kind of a sophisticated rebalancing method. And, well, it might be that they're still efficient enough to execute, but they're definitely a mess to implement. There's nice implementations of red-black trees that don't look too messy, but coming up with the implementation is quite a challenge. And randomization can not only help to overcome these defects, it can overcome the defects in a much simpler and elegant way. Well, let's see why or how. I'll show you two examples. The first is called a treap. You might have heard of that creature before. Let's start from the beginning. So you know that in a binary search tree, the in order is always just the sorted sequence of the nodes of the keys. That's by definition. If you additionally record the pre-order, then you can reconstruct the binary search tree entirely, because the pre-order is exactly the sequence of insertion. So the one-to-one, okay, I should argue both directions. Each BST has a unique pre-order, that's for sure, whereas the insertion order is not unique, as you know. There's many more permutations than trees, which also means that not all permutations are pre-orders of some tree. That's just because a pre-order defines everything from the left subtree comes before everything from the right subtree. That eliminates a lot of permutations. So every tree has a unique pre-order, and each pre-order generates exactly one tree because it's a valid insertion order for that tree. And both of these processes can be given as an algorithm that's deterministic and always produces the same result. So it's a characterization of a specific shape of a tree. So an elegant way would be that we just enforce the pre-order of some random BST while we are doing our insertions. So by some kind of magic idea, right? The problem is, of course, that we don't have a control over the set of keys that will be inserted, and we wouldn't like to restrict that. That would make it unpractical. So we have to live with the problem that the keys might come in sorted order, but we don't know that it will be like that, right? And then the key idea of treaps is, let's just add another component. We have the key values that are supplied by the user and where we don't have any control. And we additionally use ranks that eventually we will choose, but in the first step we will consider them as given. And these priorities, as we will call them in the following, are just ranks in the pre-order. So, okay, maybe they define a ranking. The priorities, as you see here, are just some numbers between 0 and 1. And then sorting the keys by their priorities gives you the pre-order. That's kind of the idea. Or gives you the insertion order, not the pre-order. This is the relative ranking of the priorities is a permutation. It's not necessarily a pre-order. I just argued carefully why this is a difference, and then, yeah. Okay, so insertion order. So we're given n such key priority pairs, and then we can define a binary tree for these pairs that we call a treap. And it has to satisfy two conditions simultaneously. First of all, it's a search tree with respect to the keys, as usual, and a heap with respect to the priorities. Let me add, it's a max heap. You could also symmetrically use a min heap, but everyone uses max heaps for treaps, so I will as well. Okay, that's a nice definition. You might, if you haven't seen that before, who's seen treaps, by the way? Okay, so close to all of you. Nevertheless, if you first see that definition, it's not even clear whether this should be, why this should be actually possible to have both of these properties. But actually, it's a simple statement to show that there's exactly one treap for any such list of key priority pairs as long as they're all distinct. So existence is pretty easy once you get the hang of what this is about. The priorities give you an insertion order, so if you insert the keys in decreasing priority order into an initially empty BST, then what you get is a BST with respect to the keys. So this is also with respect to the keys. Well, and it's a heap with respect to priorities, because we know in a BST all new nodes that are inserted are below all older ones. Not all, but all nodes on the path to a certain node have been inserted before, and that because they're were inserted in decreasing priority order, the priorities along every path from the root to any node are just decreasing. And that's another way to state the heap property. So that was existence, and that there's also at most one such tree is easy to see by induction. If you only have one key, then it's clear there's just one such tree shape. And if you have more, then the root is uniquely determined as the key where the priority is maximal. Right? And then you use the induction hypothesis on the subtrees. Which you build from all the keys that are smaller or larger, because that's enforced by the search key, the search tree property. Right? So I guess if you've seen Treaps before, you've seen this proof before, so I did it a bit in the fast forward mode. So this was nothing about randomization up to now. It was just given pairs of keys and priorities, you can always guarantee the existence of one such tree. A randomized tree is now one where we're just given the keys, and whenever we insert one, key ki, we choose the priority uniformly at random between 0 and 1, independent of all previous priorities. That means almost surely they will all be distinct, and that will give us a unique treap. And what's more, the shape of this randomized treap has the same distribution as our good old random BSTs. And this is actually easy to prove because the probability for the treap to have a certain shape. I should have introduced some notation for that. But let's stick with a sloppy version where we just write some words here. If we just have one key, then there's nothing to choose, and otherwise, well, by definition, we choose as the root the key with the highest priority. And since we choose all the priorities independent, and for almost surely don't have duplicates, any of the n keys has the same probability 1 over n to become the root. And then inductively we choose the subtrees in the same way by splitting the key set according to the root. And that means the shape of the tree has this probability, which is exactly what we had for the random BSTs. So if the probability is the same, then the distribution is the same. Well, and then we can apply all the knowledge that we spent so much time on today to derive. In particular, if you search for any node in the tree, you need essentially two log n comparisons, and you never need much more with high probability, so in this formal sense that we always had it. So in a large tree, you will almost never have this worst case as we had for the binary search trees. So you get the same benefit, the same good distribution of depths as in the random BSTs, but you certainly avoided this problem that you have worst cases, because the randomization is now by construction, by choosing these priorities. Well, so far so good, but that was only a static view. The setting was we're given the keys, and then we choose the priorities, and then we build the treap, and then we notice, okay, that's a good tree. That's not usually how you would like to use a data structure. It should be dynamic. So the question is whether we can, given a tree that was built according to whatever rule, and then has the right distribution, can we add a new key, or can we remove a key again and still get the same good distribution? And the answer is yes, we can do that. And it's actually not so hard to do. To insert a node, we just insert it as if it was an ordinary binary search tree. Then if this was a new key, we draw its priority, right? And that means we will have a tree so we inserted a new node here, that's our x, and we draw a priority for it, and it might happen that this priority is larger than the priority of its parent. And if that is the case, we simply rotate as we do it for AVL trees and all these other balanced search trees. We just keep these in order, and only have to locally change a pointer. So it's just these few pointers that you have to change in order to get this rotation done. And that means that x moved up. Now the heap order might be restored according to that edge. It might be necessary to rotate it further up. And you can do so until the heap property is fulfilled. Deletion can be done essentially the same, just in reverse. Okay, that's a tautology. Deletion is the reversal of insertion. That's always true in a sense, but you can first search for that node, set its priority to -infinity, and then repair the heap, which means now rotate down. and well, in a way that preserves the heap property. So rotating down means you have to check which of the two children has the larger priority, and that has to go up. Otherwise, it would not be a correct heap. So if you have like this, then if B has the larger priority, then you make it move that one up. And keep A down, right? And you can do that until your minus infinity is at a leaf. And once it's a leaf, you can just delete it. So this is, if you like, you can view this as a modification of Hibbard's deletion algorithm, where you also had, so the procedure was also to move a node down until we can remove it. But there we deterministically chose, let's take the smallest or largest of the subtree, whereas now we make the decision based on the priorities, which were random.
I think shouldn't the rotation be that B goes up and then to the left there's minus infinity, because now we just
Oh, you're right. That's, yeah, I screwed up. So and A is even below this.
Yeah. In the next swap, then it goes up.
Right. Which we don't want to draw. The good thing is, even without spending any more effort on analysis, you know that insertion and deletion start by searching the key, which is not more costly than the height of the tree, which we know is good. And also the rotation is bounded by the height of the tree, because in each rotation in the insertion you move x up, and there's only a certain height that it can move up, and the same for deletions. So you know that all operations are logarithmic with high probability with these implementations. That's the picture that I Googled just before class. You can actually show a much better bound. So essentially you can show that you will, in expectation, do at most 2 rotations for insert or delete, which is a bit better than logarithmic. And this has to do with this notion of a spine. And the spine of a tree, so this is your spine, but the spine of a tree is defined to consist of these nodes. So there might be more in the tree, but there's a left spine. That's these 3 nodes, and there's a right spine, which is these 3. You might, I don't know, find that is similar. So you go once to the left or to the right, and then go inwards, right? Go as close back to x as you can. And it turns out that these nodes, the number of these nodes gives you a bound on the rotations. And that's something I reserved for you to do in the exercises. So you will essentially prove this lemma here. The number of rotations in an insertion or deletion operation is bounded by, so if you delete or insert a node x, then this node has a certain left or right spine, simply defined as this number of nodes in the subtree of that node. Okay? So in the general case, this is just a part of the tree, and you're only looking at the subtree of a certain node. And then you will show that the number of rotations is bounded by the sum of these 2. Well, if you like to have a small hint, deletion might be actually a bit easier in that case, because deletion works top down. So you start with such a tree, and you can think about what happens if you if you rotate x down, what happens to the spine. And then once you found out what the connection there is, you can look at the insert step and try to find out what happens if you insert a node down here and you have to rotate it a few times up, what happens to the subtree of that node. Yeah, draw a few pictures, then you probably get the idea. What I would like to help you with is analyzing the expected values of these quantities. And this is what I referred to before. These are kind of strange quantities, right? What's the in a tree without this connection to the number of rotations, you would probably not be interested in the length of the left spine of such a node. But you can actually show that these are on expectation not even one. So in expectation you have less than one node on either side of this spine. Let's see. We will only look at the left spine. The right spine is symmetric. Now here again, it's helpful to take the kth node, not just any one, but fix the rank of its key. And then you can show this precise expectation. And I guess we should consider a picture. So here's our node K. Now the left spine is, we go once to the left and then actually to the right. And then there's one last node. And this must be the node with the key that's exactly one smaller than K. Because if there was anything between this one and K, then this would have to be in this side. So there's this node and then only a leaf. But of course the rest of the subtree of K can be much larger. And we would like to count all such nodes X that lie on this path. So I was red before, let's stick to red. In this case, we should have 4 as a result. And now we would like to express this property that node X lies on this spine in terms of these ancestor indicators. And well, you might think about this. So we certainly only have to look at X that are smaller than K, otherwise they cannot be in the left spine. Now to be in the left spine, we certainly need that X is above of K minus 1. But there are a lot more nodes potentially above of K minus 1, so we have to subtract all those that are also above of K. And if they are above of both, this is just this common ancestor thing that we defined before. And I should add here, inconveniently, we have to change our definition so that these are counted. Otherwise, you would have to add them. So otherwise, you would miss this node K minus 1. But that's not actually a problem. So what we've shown before is that this probability for this event is just 1 over and then the size of this set. And if these two are the same, then this nicely turns out to be 1. So in fact, with the old convention, we had to do a case distinction with this probability. But it was easier or more convenient to express the depth. Whereas now, with the red convention, we don't have a case distinction in the probability. Okay, you can decide which one you like better. And just to reiterate, so These are all the nodes on the path from k minus 1 up. And these are all the nodes that I subtract that are also above of k. And, well, including k itself in this case. And well, you can think about it that this can never be negative, in the sense that if this is 1, then also this must be 1, because this is just a stricter condition. It says x must be above these both nodes, so it cannot happen that this is true where this is not. So that's why this is sufficient. And well, the rest is just computation. I should have left the computation for you as exercise. But it's also boring enough that we can just do it. So here the difference, x is always smaller than k, so we can express it like that, and then the -1 and +1 goes away. And for this term we have to choose the largest of all of these, that's always x, and the smallest of all of these is always the k, the k, and then the smallest is always x, and then we have to add 1 because that was the size of the set is 1 more. And this looks like a telescoping sum. It's a bit nicer if we rewrite it in this form. So we sum in reverse. The smallest value for I that we can get, so if we insert the largest here, that's 1. And the largest we can get is, if we insert 1, then it's k minus 1. And then you see that all the terms cancel, except if you insert I equals 1, then there's a 1. That's not cancelled. And there's a cancellation, a negative term for the last one. That's not compensated for. That's the 1 over k. Well, that's exactly what we claimed. And the second part is symmetric. Fine, so treaps are actually a bit better than we claimed before. They essentially have the good properties of random binary search trees, where you can rely on the search cost. And what they do on top of that is bounded by a constant in expectation. That's pretty good. They have a few weaknesses, and that's why I want to introduce another randomized strategy as well. One thing is that whenever we inserted a new key, we chose its priority and then kept that forever, which might have the effect that a bad choice is never retained or never corrected for. But this is actually not a very, very tough problem, because many randomized algorithms have that. The second thing is that we have to store these priorities. I should mention that there's a tricky way how to avoid storing these, or at least all of them. We've also not talked about how to avoid to sample real numbers, right? So you certainly don't need that, because you never need infinite precision to decide the comparisons between two numbers. You can do something adaptive, that whenever you find two numbers that you can't distinguish up to the current precision, then you go on and sample new binary digits, in a sense. But still, in the typical way, you have to somehow store the priorities. But this storage is, in a sense, lost, because it doesn't help you in any way to do something cool from an algorithmic side. So the user doesn't have any value from you storing these random numbers, except for the good performance guarantees. I think I can very briefly give you the idea of how to overcome that. Maybe we don't do the code. So let's go back to what random BSTs were defined like. The key property was that whenever you have a subtree of a certain size, the distribution said, well, if you're sure that this subtree will be part of the tree, so conditional on that this subtree is a subtree, or this subset is corresponding to a subtree, then each of the root values for that subtree has to be equally likely. And Treaps didn't directly put this enforce that. They just achieved that indirectly through these priorities. But you can also just enforce this property whenever you insert elements. And the idea is as follows. You start with a tree that is in good shape, so it has the correct distribution of shapes. If you now insert a new node, you will insert it as a new leaf. That's how the ordinary insertion in a BST works like. And there's a certain probability that this is actually the place where this node happens to be in a random tree. But there's also a lot of other possibilities. And one thing you can do is whenever you insert a node and you pass this nodes y1 to yd, the nodes on the path. So you start here, and you go down the tree until you have your new node inserted. Then a posteriori in the new tree, this x should have had a certain chance of being the root of the entire tree, namely with chance 1 over n, where n is the new n, including this x. And even if it's not the root of the entire tree, so conditionally on that still being the root of the tree, it can have a certain chance to replace the root of this first subtree, and so on. So what you can do is just sample coins. Yeah, you see my spam messages. So you can just sample a coin with probability 1 over n, and if that turns out 1, then you replace the root. And what you will do to the tree to make this element the root without destroying the random shape of the tree is another issue that we'll discuss next time. But it's doable. And if the coin says, no, you should not replace the root of the entire tree, you go down to the next node. And you can continue like this. And you can prove that this preserves the same distribution of shapes as if you had inserted all the elements in a random permutation order. What this needs is the subtree size of each node to be stored or to be computed anew, but that would be inefficient. So you have to store something in the root in the nodes as well. But unlike the priorities for Treaps, the subtree size is actually an asset. To know that allows you to implement rank-based operations efficiently. So finding the kth smallest node in the dictionary, or outputting the 5th up to the 10th, or what else could you do? Determine the rank of a given value. That's all kind of rank-based operations that are helpful in some applications. And storing the subtree size is the well-known trick how to efficiently do these. And here we can use this subtree size to also drive our randomized process. So that was insert. For delete, delete is actually simpler again. If we should delete a certain node x here, then there's its two subtrees. Well, the case that x is already a leaf or something is boring, and you just remove it. The interesting case is if it has two children. And then you can, in the tree where x is gone, this will be a new subtree that has to comprise all the nodes of these two trees together, just without x. And the root of this tree should be chosen uniformly from all these nodes, But you don't have to really choose one of all the nodes. You can just take either C or Y with a corresponding probability. And that again gives you a tree that's in the random shape. Now if you chose, for example, Y to be the root of this tree, then there's a gap here, so you recursively delete in that subtree with the same procedure. So that's again a generalization of Hibbard's deletion method, but this time with explicitly chosen probabilities, so to enforce the shape of a random BST, where again Treaps achieve the same thing but in an indirect way by using the priorities. Yeah, so I guess you're curious by now how to actually implement these things, and we'll see that next time.